Assalamu alaikum. Our lecture for today is flexural design of a prestressed concrete element. Contents: simple case, distribution of flexural stresses during load history, load deformation curve of typical prestressed beam, and final example. Here the sign convention for flexural stresses and bending moment. We can see in this figure the sign convention for flexural stresses and bending moment. In A, negative bending moment with tensile stresses at the top fiber and compressive stresses in the bottom fiber with negative sign convention. And here in B, the positive bending moment with compressive stresses at the top fiber and tensile stresses in the bottom fiber with positive sign convention. Simple case, simply supported rectangular beam with concentric tendon, just only pre-stressing force applied to the member. Here we can see the pre-stress force in the center line of concrete and form just only compressive stresses equal to P over A with a negative signal, and here the area of a cross section equal to B multiplied by H, and here the concentric tendon additional with the last cases self weight added, and we can see the first just only pre-stressing force, then the self weight added to the member, and make the negative compressive stresses here in the top fiber and tension stresses in the bottom fiber, and the stresses equal to mc over I, and m here is the moment due to self weight. And for summation the two stresses and calculate the final stresses appear in this figure equal to the stresses at the top fiber equal to a negative P over A plus negative MC over I gross, and the stresses in the bottom fiber equal here to negative P over A due to compressive stresses, and here the tensile stresses plus MC over I gross. C here equal to the half of the height of cross section, and I gross equal to B multiplied by H rises to power 3 divided by 12. And here in this figure we can see the eccentric tendon pre-stressing force applied to the member. Pre-stress increase compression at the top fiber. Tendon place eccentric to the neutral axis, and we can see here the center of gravity of concrete, and here the center of gravity of pre-stressing stresses. The distance between the two lines equal to E, and due to transferring pre-stressing force to the center line of concrete made and formed moment equal to P multiplied by E. Here we can see the stresses due to pre-stress only, and here due to transferring the pre-stressing to the center line of concrete. And this shape we can see the result of summation of two stresses. This equation equal to stresses at the top fiber equal to negative P over AC plus tension here, PE multiplied by C over I gross, and the stresses in the bottom fiber, 2 it's negative, and summation the two stresses equal to negative P over IC plus negative PEC over I gross. C here equal to also E. Eccentric tendon, here adding self-weight to the member. This shape resulting from the previous state due to prestressing force and transferring the prestressing to the center line, and here adding the self-weight. Due to adding self-weight, the stress is equal to MC over I. Here M self-weight. We can see also this self-weight make stresses in the top fiber negative and in the bottom fiber positive due to tension, and then we can summation the two stresses also, and we can resolve this equation at the top fiber equal to negative P over AC plus PEC over I minus MC over I gross. And here the stresses in the bottom fiber equal to negative P over A minus PVE multiplied by C over I plus MC over I due to tension stresses in the bottom fiber, where here M self-weight, M dead. Distribution of lecturer stresses during load history. Here in A, we can see beam section with prestressing force, and B, we can see the initial prestressing force, tension, small tension in the top fiber, and compression stresses in the bottom fiber. And in C, we can see self-weight and effective prestress, compression in the top and bottom fiber, but the compression stresses in the bottom fiber was less than the compression in the bottom fiber. In D, we can see also compression, but this state full dead load plus effective pre-stresses, and maybe here in the bottom fiber the compression could be 0 due to decompression. In E, we can see full service load plus effective pre-stress, and the compression in the top fiber reach the maximum state, and here appear the tension in center line of a pre-stressing tendon. In F, limit state at ultimate load for under reinforced beam. Where MT equal to self-weight moment, and here MSD equal to additional superimposed moment, weight slab concrete, and also the additional loading. Load deformation curve of typical pre-stressed beam. Here we can see in this figure the load deflection curve of typical pre-stressed beam from the beginning of made the pre-stress section. In A or 1, we can see theoretical camber of beam weightless with initial pre-stress. And also we can see delta pi equal to initial pre-stress camber into theoretical camber of beam weightless also with effective pre-stress with delta pe effective pre-stress camber. Number 3 here, camber due to effective pre-stress and self-weight moment. In 4 we can see the balance state, zero deflection, uniform stresses over section depth, balance state. In 5 decompression, zero stresses at bottom fiber, here zero stresses at bottom fiber. In 6 we can see the first crack load, cracking under first loading. In 7 steel or concrete reach non-elastic behavior. In 8 steel yielding. In 9 maximum beam capacity is reached, mean the steel pre-stressing steel rupture or the member rupture. In this table we can see the characteristic of steel according to ASTM and Nu'man book chapter 2 in page 42. We can see this table in the first column, the pre-stressing steel type, stress relief wires according to ASTM A 421 and stress relief 7 wire strand according to ASTM A 416, and here the ASTM type of grid for each type of pre-stressing steel. Grid here 250 and 270, and here the nominal diameter in 2 unit inch and millimeter, and here nominal area also in inch or millimeter unit. And the final column the tensile strength for each type of steel, pre-stressing steel, FPU, also in both units, KSI or megapascal. Example. Other example also we can find it in Norway in page 19 to 27. In this section we can see all dimensions appear, and this section for pre-stress member pre-tension with FCI 3050 100 foot per inch square. Also we can see 30 strand with half inch diameter, FPU equal to 270 and span length 25 foot. Determine 1. Section properties, 2. Force acting on the section, 3. Stress at centroid of steel. Also this note, to transfer unit from foot to inch, multiply it by 12, or transferring inch unit to foot, divided it by 12, and to transfer KSI by multiply it by 6.895 to transfer it to megapascal. Solution. Compute section properties. Area of bar equal to 30 multiplied by the area of uh, half diameter equal to 0.153. We take it from the table, the previous table, and equal to 4.59 inch square. Area of the cross section, two area, top and the vertical one, by the summation of the two area, 4 multiplied by 48 and 8 multiplied by 36. We calculate also the y prime from summation area with the distance from its centroid to the centroid to the edge, the top edge of the section. Also summation this area with this area and multiply it by the its centroid to the top edge of the section, and divided the both area calculated with summation of two areas, and calculate y prime equal to 14 inch. And here we can see calculate the I gross moment of inertia of the member equal to B multiplied by H, I is to power 3 divided by 12 plus A multiplied by D square equal to this number. Compute force acting on the section. Here the self weight WD dead equal to area gross divided by 144 to transfer it from inch square to foot square multiplied by gamma of concrete 150. And here the moment due to self weight equal to 0.5 multiplied by 25 square, it's the length of the beam, divided by 8, WL square divided by 8. Here the yielding stresses equal to 0.85 from the ultimate stresses of steel, of pre-stressing steel. Here the ultimate from the example, take it 270, and also calculate the FBI, the initial pre-stressing stresses equal to minimum 0.82 from FBY or 0.74 from FBU. Here the minimum stresses equal to 188.2 KSI. And also calculate the initial pre-stressing force by multiplying the stresses, initial pre-stresses, by area of pre-stressing steel we calculated in the top. Compute stresses at centroid of steel. E equal to 26 minus 5, this 5, equal to 21. And here calculate the radius of gyration equal to I gross divided by I gross under root. Stress in concrete at level of a pre-stressing steel equal to, here stress is at the bottom, equal to negative P over AC plus negative P multiplied by E by C over I gross due to transferring the pre-stressing force to the center line, and here plus MC over I gross due to self weight of the beam. And also we can find this equation in another shape same to this one. And finally, the stress in the concrete at level of pre-stressing steel equal to negative 6.593. Thank you.